So I'll be talking about castle reliability. I'm an architect in the engineering. So first, what is castle? Castle stands for a cache accelerated sequential layout. It is the engine of our system. This is what determines how data is laid out on disk. This determines how reads and writes are handled. This is how internal operations are handled, such as garbage collection or all the scale out logic, snapshots, replication, all of that. So this is the heart of the system. So in order to have a reliable system, there are certain principles that have to be followed, and they are more important than anything else. The first one is integrity. That is, don't return incorrect data. That is, when some data was written to the system, what is later read from, when it's requested from, has to be returned exactly what is written. The second one is the durability. So that's don't lose data. That is, if there's some data was saved to a system, later we turn around and try to request that data, it better be there. System cannot say, sorry, I don't have the data. So that's kind of obvious thing. And the third one is availability. That is, don't lose access to data. So that the system still has data. That's a difference from the two. But not now. It's not available right now. The system is down. So we can't have that. So for data integrity, that is, don't return incorrect data. The goal is to ensure that we always return exactly what was written to the system. However, the operation on this can fail in multiple ways. And so some of the ways, it's simply that the read or write operation can fail. And that is, the drive didn't perform the operation, return an error instead. So it's a fairly common failure mode, so most storage systems deal with it. And we also deal with it. I'll describe how. A more tricky failure is when the drive corrupts data. So that when the drive writes to the media, the data in a drive ends up incorrect, or perhaps on a read, the return data is incorrect. So we have to deal with that. There are certain ways of protecting from this kind of failure. And the better systems deal with this kind of errors. Now, there is one more insidious way of failure, and that is when the drive says, in the second one, the drive said everything is OK, but the data return was incorrect. In a third failure mode, drive says everything is OK, but just the drive, for example, on the write operation, perhaps it just didn't perform the write operation at all. Or if maybe it wrote to the wrong location. Or another thing, when the read operation comes, maybe the read came from a wrong location. So some of the techniques to protect from the second mode of failure, they don't protect from the third one. So to protect from these kind of failures, we use checksums and self-IDs. So every time a data block is written to the storage, to the device, we store with it the checksum and the self-ID. And every time the data block is read, we read the checksum and self-ID, and we verify them, that they match with what we expect. And we do it every time. It's not a subset of blocks, we'd say some most critical blocks, like some metadata blocks. It's all the blocks. And on the reads, we do it every time we read the data. It's not a subset of blocks. It's not some sample, percentage statistical sampling. We do it every time. How can we do that?
Where's the checksum generated? In the data path?
Yes, it is in the data path. We actually have various checksums that are in the system.
This is the checksum that's actually stored on the flash of the disk, right?
On the disk, that's right.
So where is it generated?
It's generated inside of the castle as the data arrives from outside.
So it's a software-generated checksum?
Yes, correct. So how can we do it every time? That is, it is the sequential layout that allows us to do it, so that we write data on disk in a long sequential writes where multiple blocks are packed together. The blocks are compressed, variable size. They don't have to be aligned to sectors or anything like that. So it's very easy to add another variable piece of data, additional checksum or self-ID. Now, checksum obviously helps us detect the corruption. And the self-ID helps us detect the misdirected writes. I will explain in the next slide in a diagram. Now, occasionally, so those failure modes, 2 and 3, they are not very frequent. They are rare. However, if they happen, they don't match. We would reconstruct the data using the RAID parities. We return the correct data, and we fix it on a disk. And by the way, first time before we reconstruct, we retry the operation again in case it's just an error on the read. And second time, the read is going to be directed to the correct location, is going to return correct data. So here's a diagram that explains this. So this faint, barely visible cylinder is the storage. There is a write operation, write to some offset or LBA, logical block address, and there's some data with it. So we write the data to the disk. We compute the checksum, and we write the checksum with the data. We also write the self-ID, self-description, self-ID of that block. Now, in this case, I simply just, I didn't have much room, so I just wrote the LBA here, but actually there's much more information that we store because there are multiple lines or volumes, the same LBA could have the same, there are multiple, there are snapshots that are different versions of data and things like that. The metadata has a self-ID.
So you guys do dedupe?
No, we don't do. Let's say a read operation comes, reads the data, we read it to the buffer. We compute the checksum. We compare it with the checksum on disk, it matches. We compare the self-ID, it matches. So this is the good case. Now let's say this data becomes corrupted on a disk. So this red letter shows corruption.
It's a single bit.
So then we read it. We compute the checksum. And we compare the checksum, doesn't match. We reject that. And we are going to perform these recovery steps that I mentioned. So this is the one failure mode. Another failure mode, let's say there is some other data, unrelated data in a different location on disk. The read comes, and let's say the read, the drive directed to the wrong location. We compute the checksum. We compare the checksum that came with that read, matches. So the checksum didn't protect us from this kind of failure. Then we compare the self-ID, and that's what saves us here. We find a mismatch. Another failure mode is when the write went to the wrong location. So we expected to write here, and the drive wrote to the wrong location. Here, we read it from the location where the data is supposed to be. We read some data, we compute the checksum matches, but again, the self-ID doesn't match. And then we perform the recovery. Similar things would happen if the write simply wasn't here, if the write was dropped. Or similar thing would happen if there was
Although recovering from a dropped write is more difficult.
It's very similar, so we use RAID to reconstruct it, to recover it, just like in all the other failure cases. Another thing, there could be another write that's scribbled on this data. Would be a very similar thing would have happened. So there are other checksums in our system for all the data that is sent between arrays. For example, for replication, for disaster recovery between the distant data centers, for a scale-out cluster when there is one pool that spans multiple arrays, and for example, we have to move some data between the arrays. Why would we move data between arrays? So in scale-out, if you want to grow the scale-out pool, you will have to add an array. It's empty. Now some data has to be migrated to that. So all the data is protected and checksummed. Or let's say for some reason, our scale-out scales linearly. The performance scales linearly. We do it by having initiators send the data to the correct array, the data that has to the array that has the data. If initiator, for whatever reason, sends to a wrong array, we would redirect it to the right array. It's all protected by checksum. Or let's say if somebody wants to move a volume between the two pools, they would also, the data is protected by checksums. However, that's not enough. There are some higher level checksums that that cover a larger data sets, up to an entire volume or snapshot. We can do it very efficiently. And that could detect some failure cases, for example, when some data is copied for replication or volume move from one array to another array. If we checksum every message is correct, but how do we know all the messages went through? So there is an entire checksum can verify consistency over everything. The second principle, durability. So don't lose data. However, drives fail. So we can protect from that. When the drive failed, the data on the drive is lost. So the RAID protects from that. However, drives become very large. So, and at bit error rates, the unrecoverable error, read error rates from drives stay about constant. The size increases. So now, during RAID reconstruction, the chance of unrecoverable read error is no longer acceptable. So with NimbleOS 1.x, we offered double parity RAID, and we do it without performance impact. I will explain how. So here's the diagram that describes it on top. So it just shows 6 disk drives, but that's not necessarily the RAID size that we use. Now others at the time offered double parity, but as a choice and with a performance caveat. That's why there was a choice. For us, there's no need to give it a choice. With NimbleOS 2.1, I think, we offered triple parity RAID. So there are 3 parity disks now there. But this is, anyway, it's not disks. This is a RAID stripe, and this is just depicts 1 stripe on the disk. So, and we do it without performance impact. It's orders of magnitude more reliable and can protect these kind of large drives. And it is the sequential layout again that allows us to do that efficiently. We can use space-efficient parity RAID as compared to, say, mirroring, which is not space-efficient. And we can support it for all workloads without any performance penalty. So that the reason is that the parity write, we can amortize it among thousands blocks. So otherwise, with write 1 block, compute parity and write parity, another block, rewrite the parity. Instead, we write entire stripe, many, many, many blocks, and we write parity once, thousands of blocks. Now, others offer a choice of parity or mirror RAID, but with the caveat that mirror RAID is required for a most performance-sensitive workload, and that is not space-efficient. We also store additional parity. So here, with each chunk in the RAID stripe, that's in intra-drive parity. Now, all these multiple parities and checksums, they allow us to recover from extreme error conditions, and it is more than what most other storage systems can handle. The third principle, availability. So don't lose access to data. We have a greater than 5 nines, 99.999% availability.
Going back to our last topic.
Yeah.
How frequently do you background scrub?
Yeah, we do have background scrub. We have a guaranteed time. I don't remember right now the time. I can tell you afterwards.
That's fine.
I will have to check with somebody.
Yeah.
Yeah, it's very important. Yeah.
Yeah, because if you had a dropped write, you want to find out about it before you're doing a RAID rebuild.
Yes, yes, that's right. So this 5 nines availability, it's not just a claim. We actually measure it across the field. And we measure it across all possible arrays. It's not just a subset of arrays, because you could pick a subset of arrays that just happens to have a high availability. It's across all the arrays. And we have a white paper on it that is available on our website, so anybody can check our methodology. What are the factors that allows us to do this? One of them is the hardware, obviously, no single point of failure. And the second one is the castle, so that we have a high availability. We use active standby controllers, and a failover gives us the high availability. The failover could be then managed, let's say, during upgrades, or could be unmanaged, say if there's some component failure or somebody pulls a controller. The third factor is InfoSight. So I think we talked about it extensively by doing all the monitoring, data analysis, failure prediction, and intervention. And the final one is the processes. So that we have a very tight loop between support and engineering for case analysis, for all the InfoSight analysis, and so on. Now, occasionally, if a failure occurs, what do? We get immediate alert through InfoSight, and we recover the system as quickly as possible. We also inoculate others when we find out how it could be done with workarounds and with messaging. So we'll talk about blacklists, and we can have other techniques too. And InfoSight allows us to target who is susceptible to this issue. And we fix the root cause. And often for fixing root cause, as it was described, we use InfoSight to find to do the investigation. Another thing that allows us to claim this availability is non-disruptive upgrades. So that hardware upgrades, the firmware upgrades, and even entire arrays could be upgraded through scale-out, so that one can bring another array to the pool, move the data from one array to another array, and then evacuate the old array. Everything non-disruptively. There's no outage. And as we talked about it, upgrade the majority.
Tomas, with a log structured file, you need to have some sort of a mapping structure that maps the customer volume address to the physical address on the back. How is that protected and recovered, and not lose any data from that?
That's right. So it's protected by all the RAID. It's protected by all the checksums, and self-ID has the full protection, the same protection as the data has. It's protected by all of that.
That structure.
Yes, the metadata is also protected. Yeah. It's very important because if you lose a chunk of metadata, it can amplify and you can lose a chunk of data. Now, in addition to all those three things, the integrity, the durability, and the availability, we also protect. So those are they protect from failures that we can call it failures within the storage system. Now, we can also protect from external risks. So, for example, and we can do it efficiently. So, for example, if there's a user error, application errors, snapshots are used to recover that. If there's a disaster, say fire, flood, or some power outage, we use replication to a remote data center.
And the snapshots are copy on write or redirect on write, or how?
Redirect on write.
Redirect on
That's right. And I'll talk a little bit more about snapshots. And data theft is another external risk. So we offer encryption to protect from that. So snapshots, just what you mentioned here. The snapshots are embedded into the data layout and index from day zero, and without any performance penalty. And another thing, they preserve write order locality, temporal locality. They are space efficient. We have a user can choose application-specific block size. The snapshots are compressed and can be on disk. They don't have to be on flash. And they offer protection at very little cost. Basically, the primary cost is the space. There's no performance penalty, and it can be controlled by attention. So pretty much, there is no good reason not to use snapshots. If somebody's not using snapshots, they are losing on a really important protection.
So a snapshot can be a different block size than the original data?
No. Different volumes. Different applications use different block size. So when a volume is created, user can specify the block size, and it stays with the volume.
And the snapshot's on that same volume?
Yeah, snapshot is on the same volume, of course. And user the same
compressed, you're talking about data compression?
Yes, data compression. Every block in our storage system is compressed. As we store it, it's compressed. The compression, the reason, again, what allows us to do it is the sequential layout. Because we don't have to worry about sector boundaries in trying to fit the data into the sectors. We have a very large striped, very long sequential write. We can pack blocks tightly, even if they are variable size, because compression gives us variable length blocks.
Right, and an arbitrary number of blocks depending on how the data compresses.
Mm-hmm. Yes.
Yeah.
That's right.
Yeah, we've pretty much reached the point where there's no reason not to compress.
Mm-hmm. That's right. Right. And these days, there's plenty of CPU power.
And decompression is very inexpensive.
That's right. Decompression is even less uses even less CPU power than the compression. Yeah.
And it's compressed in line.
Yes, in line.
Yeah.
That's right. So
over the encryption a little bit, since that's a rather
yes, I'll
new
talk
feature.
about the last thing. Yeah. So replication. Replication uses compressed blocks, just as they are stored on disk compressed. So we don't have to compress them in order to transmit them remotely. So it's bandwidth efficient. And we use a non-chatty protocol such that tolerates large network latency. Large network latency is not a problem for replication at all. And finally, encryption. So encryption is global or per volume. There's an on-off switch. And we use per volume keys. And encryption traffic is also replicated for encrypted volumes.
Does it support external key managers?
No.
Okay. Is there any plan for any sort of OASIS or anything like that?
I cannot talk about future, so.
All right.
Darn public companies.
All right, to summarize, those are the 3 principles and data protection that we saw. Integrity, non-return incorrect data. This is actually the most important principle. The second one, the durability. We must not lose data. The availability, not to lose access to data. And the protection, additionally.
So replication is synchronous or snapshot replication?
Snapshot replication.
So it's asynchronous.
That's right.
And what's the periodicity for those snapshots?
So user can specify periodicity.
The minimum granularity.
Minimum granularity, I don't remember. It's is it 5 minutes or was it?
I think it's 2 minutes. But we
2 minutes?
Many customers doing 5 minutes, 15 minutes. There's some
15 minutes is the standard answer, so less than that is good.
Yeah.
Okay. Okay. So
Now, since you guys send up a lot of information to InfoSite, is the encryption key sent up that users specify?
No.
Just had to ask.
The right reaction, including the facial expression. It's just like, no, but it would be shocked if yes.
So the point being, if you lose your encryption key,
oh yeah, if you lose encryption key, the data is gone. So actually, users don't manage encryption keys directly today. They manage passphrase. If you forget your passphrase, cannot access those encrypted volumes. And we have different settings for encryption. So, for example, when an array comes up, for full security, the key would not be stored anywhere in the array. User will have to enter the passphrase. There is a second mode. Some users want some protection, but they don't want this inconvenience of having to enter passphrase in case array just comes up after complete, let's say, power outage. So there's an available mode where the key is stored in a, I don't know how much detail I can say. It's not stored on disk. It's hidden somewhere else.